Hey everyone, and welcome back to The Explainer. This one is brought to you by Forge College. So, in our last session, we totally mastered the art of testing entry points locally, right? We built the scaffolding, we mocked out the instruction data, and we isolated those failing behaviors. But, having a flawless test suite is kind of like having a perfect blueprint for a machine that, well, doesn't actually exist yet. So today, we're putting on our hard hats. We're going to actually build that machine. We're going to write the modular entry logic that satisfies all those local tests we just finished writing. Let's get into it.
Okay, so look, there are basically two ways to build a Solana program. On the left here, that is monolithic spaghetti code. This is what happens when you just mash your parsing, your runtime logic, and your math, literally everything, into one giant file. And let me tell you, when it inevitably panics on the blockchain, you will have absolutely zero idea where the fire even started. It's a nightmare. Now, on the right, we have beautiful, clean, modular logic. This is our goal today, folks, a highly organized, easily testable assembly line that's going to keep your debugging sessions incredibly short.
So here's our engineering blueprint for today. We're going to quickly cover the entry point blueprint, organizing Rust modules, Station 1, the parser, Station 2, the processor, a real-world application, and finally wrap it all up with a recap and next steps.
All right, let's kick things off with Section 1, the entry point blueprint, where we map out the Solana program class.
I want you to think of the entry point file as the front gate of your factory. Or, actually even better, think of it like a somewhat lazy bouncer at a club. It really shouldn't be doing any heavy lifting or complicated math. Its literal only job is just to exist right there at the front door, welcome the incoming data, interface a bit with the Solana runtime, and maybe translate a couple of errors on the way out. It is strictly just the glue.
Moving right along to Section 2, organizing your Rust modules, or laying out the factory floor.
Okay, so here is the perfect, pristine, three-part structure for your crate. First up, we've got entrypoint.rs. Like we just said, this handles the runtime glue, things like your process instruction function and basic logging. Next is instruction.rs. This is your parsing and validation layer, which houses the instruction enum and your unpack functions. And finally, processor.rs. This is where the actual magic happens. The state transitions, the pure domain functions, the arithmetic, the real meat of your program.
Which brings us to this massive golden rule in engineering. Keep Solana runtime specifics isolated near the entry point and keep business logic pure. Why is this so absolutely crucial? Well, pure business logic doesn't actually need a complex blockchain environment to be tested. If your math and your state transitions are totally isolated, you can unit test them locally, instantly, without having to spin up a heavy runtime environment. It's an absolute game changer.
Let's zoom in a bit. Section 3, Station 1, the parser, or as it's known in instruction.rs, the mail sorter.
So, the outside world is constantly hurling raw, sometimes totally chaotic bytes at your program. The instruction parser is this highly focused layer that looks at those raw bytes. Usually it just peeks at the very first byte, which we call the discriminant, and uses that to unpack the rest of the package into a clean, strongly typed Rust struct, like transfer params. And if the bytes are just garbage and don't make sense, it immediately throws a testable parsing error.
But hold on a second. Here is a question for you. You've got your bytes, right? And you've neatly turned them into a beautifully typed Rust struct. The parser did exactly what it was supposed to do. But is that data actually safe to just send down to the factory floor?
The short answer is no, not until we validate it. Step 1 is unpacking the bytes, sure, but Step 2 is the really crucial part, validating the layout and the length of that data. You have to ask, does this byte array match the exact length we expect it to? If it doesn't, we don't just let the program wildly panic. No way! We move to Step 3 and return an explicit, clean error. This ensures our local tests will happily fail immediately and tell us exactly why, which is exactly what we want.
All right, data is validated. Section 4, Station 2, the processor. Welcome to processor.rs, the actual factory floor.
Now that we're on the actual factory floor, safety is absolutely paramount. And that brings us to checked arithmetic. Inside processor.rs, you should always be using safe functions, things like checked sub and checked add. Because think about it, if a user tries to transfer way more tokens than they actually have, we do not want our program violently panicking and crashing. We want it to catch the math error and return a clear, graceful domain error.
So this safe math ties perfectly into the processor's full list of duties. It receives those perfectly typed instructions from the parser.
It applies the state transitions, performs that pure arithmetic we just talked about, and then returns rich, highly descriptive domain errors if something goes sideways. And it's only at the very end, at the outermost boundary of the entry point, that we actually map those rich domain errors out to standard program errors.
Let's see how this all connects in practice. Section 5, Real-World Application, Integrating with Local Tests.
Okay, here is our real-world transaction workflow in action. First up, we parse the raw bytes into our instruction enum. If that works out, we slide over to step 2, validating the accounts and ensuring the right people actually signed the transaction. Passing that? Awesome. We hit step 3, checking numeric bounds and processing the state. Setting it up like this creates a beautifully rigid fail-fast pipeline. If a test fails, you know instantly which step caused the issue. No guessing required.
And guys, this brings us right back to avoiding unnecessary pain. On the left here, we have the dreaded late-stage runtime panic. I mean, there is literally nothing worse than trying to debug an explosion deep in the bowels of an unstructured program. But on the right, failing fast, the absolute joy of finding a neatly localized parsing mismatch right at the front gate, caught instantly by your unit test suite. It's a beautiful thing.
Let's wrap this up. Section 6, Recap and Next Steps, Preparing for Production.
Look, if you take away absolutely anything from this explainer today, let it be these 3 golden rules. 1. Always parse your raw bytes into explicit, testable structs. 2. Fail fast on your canonical validation to drastically reduce your cognitive load when you're debugging. And 3. Keep your processor functions incredibly small and pure. Let the entry point handle the noisy runtime stuff. This modular assembly line approach is the ultimate secret to building pristine, reliable smart contracts.
So what's on the horizon? Well, in our upcoming lesson in this module, we're going to cover debugging entry points and common issues. But before you jump into that, I highly recommend running your local test suite right now. Try implementing this modular structure we just talked about and jot down the names of any failing tests you bump into. Having those real, concrete examples ready is going to make the next debugging lesson incredibly powerful for you.
And I'll leave you with this one final, slightly provocative thought. Even with this beautiful, perfectly modular, rock-solid unit testing setup, what hidden runtime bugs might still manage to slip past the gate? We are going to uncover those exact edge cases next time. Thank you so much for joining me on this explainer, brought to you by Forge College. To continue mastering Solana, Web3, and way more, be sure to head over to Forge College to access some amazing educational resources. Keep building, keep testing, and I will see you in the next one.